Novel waveguide technologies. 3D printers were invented in the 1980s, and their applications are spreading rapidly. Originally known as rapid prototyping machine, a 3D printer is a molding machine that specializes in rapid shaping. In recent years, the price of 3D printers has reduced, and home-use 3D printers based on thermal melting lamination are also available for sale. Moreover, for business use, machines that employ the inkjet method, optical shaping, and powder sintering molding are used in the development department of the manufacturing industry. Because 3D prototypes can be made without a mold, they can be made using simple prototyping. Various reports have been produced on prototypes of waveguides and peripheral components made by resin molding 3D printers. Because electromagnetic waves cannot be confined in plastic tubes, it is necessary to make additional conductive membranes on the surface of the pipe. Thus, although a film having high conductivity can be formed by the plating method, the film thickness is approximately 1 mm, and so the microwave penetrates into the inside of the film before finally being transmitted. Thus, adequate shielding properties cannot be obtained. There are also examples that employ a conductive paint to achieve a film thickness of approximately 10 mm, however, the conductivity is poor and the loss due to the conductor becomes large. Moreover, these are mainly microwave components. For millimeter wave components, fine processing is required, which is difficult to realize with the current processing precision. Moreover, evaluation of several resin materials of the acrylonitrile butadiene styrene such as the resin used in the optical fabrication method revealed that the value of the imaginary part of the dielectric constant, which is a factor of the loss of electromagnetic waves, is relatively large. In the future, it is desirable to develop low-loss materials and molding methods for microwave components. Moreover, 3D printers capable of directly molding metallic materials are also being used. Metal powder can be sintered by selective laser sintering or selective laser melting. As a result, processing of the conductive film and losses due to resin are eliminated. However, unevenness is formed on the surface, and there can be a problem with the surface becoming very rough. As surface roughness decreases, the conductivity of the surface decreases, conduction loss increases. Currently, aluminum alloys are mainly used in 3D printing as materials, but a practical use of copper-based materials is progressing. If the conductivity of the material improves, this loss can be expected to decrease. We fabricated a 10 GHz rectangular waveguide and evaluated its characteristics. As a result, there was a transmission loss of approximately 1.5 times than that of the usual waveguide. There was also a leak from the flange portion. The connection was improved by polishing unevenness, but additional work is still required. A. Metallic rectangular waveguide and B. Polished surface. Weight reduction of the waveguide is done by using resin, but the structure of the waveguide has remained as a non-hollow, solid pipe. Therefore, we are developing a flexible waveguide that is like a water hose. Besides improving convenience by making the pipe flexible like a hose, the image changes and the application range may expand. We introduce an example in which a waveguide is made by winding a copper foil in a hollow resin hose. Our waveguide is a hollow, soft resin hose with a conductive coating on the outside for electromagnetic wave transfer. Conventional metal waveguides undergo passage, return, and conductive losses, which should be reduced as far as possible. Resin waveguides generate additional dielectric and radiation losses. The dielectric losses are due to absorption by the resin, and radiation losses occurs by leakage due to the insufficient shielding of the thin film conductor. Dielectric and radiation losses are the dominant loss components in resin waveguides. Loss factors in the resin waveguide. In this study, we use a soft elastomer material with excellent properties for forming flexible waveguides. In the 10 GHz band, the relative permittivity and dielectric loss tangent of the resin R epsilon R equals 2.28 and tan delta equals 0.00072, respectively, ensuring very low losses as in a Teflon. Conversely, the conventional metal film deposition techniques of plating, sputtering, and vapor deposition are limited to conductive films with submicron thickness. The required thickness at 10 GHz, estimated from the skin depth relationship, is at least 10 mm. Therefore, the film in our prototype was formed by winding an 18 mm thick copper foil around the aforementioned resin hose. We investigated several types of foil winding and found that the lowest radiation loss occurs in the H-center configuration of the waveguide. The prototype weighs 67 grams/m and costs $1.30 per meter, enabling a lightweight and inexpensive waveguide. The waveguide has a low loss and low emission, with a transmission characteristic of -0.39 decibels/m in the 10 GHz band. Hose-type waveguides. In future application to automated vehicles, it is necessary to install various sensors, for example, high-quality inter-vehicle cameras that requires transmission speeds on the order of several Gbps with high security. Conventional wire harnesses cannot tolerate external noise in transfers on the order of several Gbps. Because the influence of noise increases with transmission speed, we believe that it is necessary to review the transmission line design. As shown in, the proposed waveguide is laid from the front to the back to transmit a camera image. The camera image was transmitted inside the waveguide by using high-speed communication between sensors. Inter-vehicle communication system. Research on two-dimensional communication by using electromagnetic waves that propagate in a thin sheet is progressing. It is assumed that the communication distance is up to several meters. Moreover, by placing a type of antenna known as a coupler at an arbitrary point in the sheet form, close proximity communication inside and outside the sheet can be made possible. It uses evanescent waves that ooze out of the sheet. The evanescent wave is an electromagnetic wave propagating only near the surface of the sheet. In this way, the sheet-shaped waveguide does not require wiring for each sensor terminal and does not radiate electromagnetic waves to space. In addition to contribute to improving communication security, a relatively large power can be transmitted without exposing people or objects that are not close to the seat to a strong electromagnetic field. Applications for wireless power transmission are also under consideration. Moreover, in the case of Japan, standard specifications for wireless power transfer in the seat are also in place. For future applications, a power supply for a car while in motion and wearable sensor devices are being considered. Sheet-type waveguide. The conventional waveguide is a high-pass filter and cannot transmit bands below the cutoff frequency. However, if the structure can be revised for direct current, DC, propagation, then high-power transmission becomes possible with a sufficient pipe thickness. We also consider that if a stop band sufficiently far from the pass band can be transmitted, then we can achieve low-frequency communication and sharing in addition to broadband communication. We propose a waveguide with a divided structure that operates not only in a conventional, A, but also in DC, B, and parallel line, C, modes. Subsequently, we investigated whether the waveguide realizes DC in DC mode and can transmit the stop band in a parallel line mode. The conventional mode is a TE10 mode, and the parallel line mode is a TIM mode. It is known as DC waveguide. Propagation modes of the split waveguide. Although the result differs from simulation results, transmission in the stop band was, at least to some extent, experimentally confirmed. In DC mode, the resistance was approximately 0 ohms, confirming that high-efficiency DC transmission is also possible. Measured results of DC waveguide. In future work, we will assess the performance of the waveguide in industrial applications. Such plural transmission modes are desired for high-power transmission and broadband communications in automatic driving. A conventional waveguide is a non-planar three-dimensional circuit, and it is a challenge to fabricate such a waveguide in bulk. CUs act as an alternative option to conventional waveguides. CUs are planar structures fabricated using metallic via hole arrays connecting the top and bottom ground planes of a dielectric substrate. A non-planar conventional waveguide can be modeled into a substrate integrated circuit. They are compact, lightweight, cost-effective, and easy to fabricate. Microfabrication of CU of several microns is also possible, and usage in the terahertz band order is also expected to be promising. Configuration of in-CU structure synthesized using metallic via hole arrays. An example in which a resonance structure is provided in a tube like a conventional waveguide to form a band pass filter has also been reported. We also report an example of fabricating band stop filters with stacked waveguide structures by CU. When the microwave is input to the CU filter, reflection occurs due to a mismatch of the characteristic impedance at the input portion.